I am Miran Domajnko from RLS. My role is product manager, and here we develop and produce encoders. So with this presentation, I would like to take you on a journey on how to choose the right encoder for your application. It should take about 15 to 20 minutes, this presentation. So maybe just for a start, an encoder is a high-tech measuring device that helps machines understand how much something has moved or rotated, or where each part of the machine is positioned. It consists of a read head and a carrier. So as a encoder manufacturer, we have many different customers and they have many different applications. But for today's presentation, I would like us to step into the shoes of someone who is building a system, a device which needs encoders, and see how the process of choosing an encoder would look like. So for the sake of this presentation, let's say we want together in this group to build a collaboration robot. We have the other components, the general idea, and now we would like to choose an encoder for our robot. So first thing that comes to mind, we're not building a 3D printer to have some linear movement that we need to measure. We have joints of the robot which will rotate. So first thing we'll choose is, okay, we need a rotary encoder. Then the next step, we have two types of rotary encoders. We have the on-axis and the hollow shaft one. So as we think of our robot hand, we need wires to pass all the way to the end of our hand, and the hand will be moving, joints will be rotating. So to have wires safely inside, traveling through the robot hand, we want a hollow shaft encoder, so with a hole in the center. So that's another criteria where we will narrow down the choosing of our encoder. This then we move to the next step and we ask ourselves, do we want an encoder with a housing or an open PCB encoder? Housing will obviously protect our encoder, but it will make it slightly bigger and it will mean additional cost. So if our idea is to have a shield around the arm anyways, so a housing, then we don't need additional housing of the encoder. So in this case, in our case, the best option would be to choose an open PCB encoder and save money we would spend on the housing. For some other application, maybe housing would be a definite must. With this, we move on to the dilemma of choosing whether an absolute or incremental encoder. And encoders tell position similar to how we tell time. We can say it's exactly 5:25 p.m. by looking at a clock, or using a stopwatch, we can say exactly 5 minutes have passed since we started this exercise. So an absolute encoder can be compared to a clock because it reads the unique position, some pattern of a scale, in our case a ring, and therefore knows the absolute position. And we want to have the absolute position here because when we turn on the robot, we want to know straight away what's the position of our robotic hand. We don't want just to track the movement or do some initial routine to know where we are and then start calculating and counting movements. The position of the encoder can be measured using various physical principles. the information can be transmitted from the carrier to the read head via light beam, an electric current, electromagnetic field, induction, etc. And again, looking at our example for application, we might face some oil inside, dirt, heat, vibration. And also we, of course, want an appropriate candidate in a performance and price range for this application. And the popular solution for such collaborative robots are magnetic encoders. So we move on and we can say we have narrowed the encoder portfolio so much already. We already look at two candidates, two specific encoders, and we can see that one has 14-bit resolution, the other one has 21-bit resolution, so and a bit higher accuracy, but it's also more pricey. So which one should we use? Apart from this, we have both match all the criteria we have selected so far. So maybe to stop here and say a word about how we look at performance at encoders. So the example of the 21-bit resolution, this would have in total more than 2 million steps within a full 360-degree of rotation. The accuracy is a measure of how close the output is to what it should be. So comparing it to a target and shooting with arrows, we see that the first arrow at the top, the first target, it's quite accurate, but the results are not very repeatable. The second target, we see that the results are repeatable, but not very accurate. And then the optimal would be to have accurate and repeatable results. And choosing an encoder, we have to be smart about chasing these criteria in relation to price and what of those features is the most important for our application. Going back to our example for collaborative robot, turns out that this example of Axim encoder with up to 21 bits of resolution is a perfect match of price and performance for the example that we are discussing. Then we move to additional specifications, and we still have to choose a communication protocol. So this is how the encoder will send us information about the position. Then we have to consider size and geometry, and ideally we would find an encoder from a catalog, a size from a catalog, and this would simplify and make the design cheaper. But sometimes we could also design our product around components such as encoders, or the further way is to have a customized encoder, either a totally custom encoder or some minor customizations. Environment, of course, we have to consider the speed, the temperature, resistance against chemicals, and vibration, shock. And then we move also to the topic of safety and redundancy. So sometimes maybe having just one encoder to measure position is not enough, and we want two encoder or one double encoder at the same spot for redundancy. Or we might need safety integrity level, a certified encoder. Additional features we can also consider with encoders are whether we're taking a single turn or a multi-turn encoder. In case we decide for a multi-turn encoder, not only we will know the exact location within the whole rotation, but also be able to count the rotations. Self-calibration is also a possibility where after mounting, because of eccentricity, we can receive some error on our accuracy graph. And with self-calibration, we can eliminate this error or reduce it very much, correcting the error that came from this not perfect mounting. Diagnostics are also to be considered. Is it enough for us to have an LED blinking red, green, yellow and observe the encoder in this way, or more advanced with software? And zeroing is just the possibility of setting the zero on exact spot where we want it. So like this, we have reached more or less the end of, we have considered all the options. Now maybe just to show, since we can have this presentation for every possible application, I would like to invite you to the RLS website, where on the encoder selector, I will just add a pointer. If you click on this button here, you get to encoder's selector program, and you can basically go through this process that we have just done now during this presentation, but for any other application, and you will of course end up with different results. So we have chosen the rotary encoder in this presentation, and then if we click on absolute, as we did here, we said hollow shaft. I cannot click, doesn't switch slides, so I'll click below, and then we would have a list of candidates, and then we have to consider all the additional things we have discussed in the last slides. So feel free to welcome and go check this selector on our website. And with this, I finish my presentation and see if there are any questions.